Okay, welcome everyone. We'll continue with our morning program. And the first speaker is Leron Borsten, who will talk about homotopy, algebras, and integrability. Thanks, and please go ahead.
Okay, thank you. Well, first of all, thanks to the organizers for the invitation to be here. It's my first time in this wonderful city and at this very nice conference. So I feel very lucky. I'm going to talk to you about homotopy algebras and integrability. I thought I would start with some kind of 30,000 meter perspective on why anyone would care about homotopy algebras in the context of field theories. I drank the Kool-Aid a long time ago, but I suspect many of you are not even close to being convinced. So I'll spend a little time talking about that, and then I'll tell you the plan for the rest of the talk. So from the mathematical side, this story goes back at least to David Hilbert and his realization that if you want to consider polynomial equations with coefficients over some polynomial ring for some field K, that there's no linearly independent basis of solutions. Rather, you have relations amongst solutions and then amongst the relations themselves in a tower that goes all the way up to R+1. And he realized you could package this into an exact sequence. So here we've got some A module E, and then we've got the space of relations and then relations amongst relations. And you can encode all of this data into what's called the resolution or the free resolution of the module E. Okay, so that's the first big idea from long ago, that really, when we're interested in some mathematical object, we should really identify it with all of its resolutions. There isn't a unique one. How would you pick one? You just identify it with every single one. You push this a little further, and then you realize that there is non-trivial cohomology in non-zero degrees, and that leads you to consider not just these resolutions, these exact sequences, but rather complexes up to quasi-isomorphisms. And I'll explain a little more what those words mean in a moment. And that lands you in the setting of derived categories. So you'll get some feeling what I mean by derived objects as we go through the talk. All right, so that's the kind of mathematical point of view that I'm taking. And then why does this connect to the physics? Well, I want to argue that we've really been in this derived setting all our lives as physicists. What we actually do in, say, particle collider experiments is we measure correlation functions, which are compared to scattering amplitudes. And these are kind of the physical objects of interest, these not correlation functions, cross-sections, I'm sorry. But of course, these cross-sections and scattering amplitudes are subject to lots of relations and relations amongst those relations. And I'm trying to invoke this idea of packaging the objects of interest together with all of their relations in a bigger object. And I want to argue that that's exactly what quantum field theory is. So there's this old quantum field theory story, i.e. the one you'll find in any textbook, where you start with some quantum field theory that's deduced from some classical field theory. You'll run through the Feynman rules and you'll learn how to compute scattering amplitudes. But you can take another point of view, this kind of on-shell paradigm, which is really a reinvention of the S-matrix program, but elevated in various different ways, where you start with the objects of interest, the scattering amplitudes, and you declare that they're fundamental. These are the true objects. And our quantum field theories are then deduced. The space-time emerges from these fundamental things that we measure. And what I'm really saying is that you shouldn't think of these as two different pictures. They are the same picture. Scattering amplitudes, our objects of interest, and are related to the quantum field theories, just in this sense of the quantum field theories are the set of all possible resolutions of these scattering amplitudes. So that's the kind of very big stratospheric point of view that I'm taking. Okay, so here it is in one slide. I want to advocate that at least in certain contexts, maybe you just want to stick to perturbative contexts, that in particular, L-infinity algebras up to quasi-isomorphisms are equivalent to perturbative quantum field theory up to physical equivalences. So that's the kind of picture that I have in mind. Where an L-infinity algebra is one of these complexes identified up to quasi-isomorphisms with some algebraic structure on top of that. Okay. So the plan for today is to introduce homotopy algebras and quantum field theories, in particular, how they get related through the Batman-Vilkovisky formalism. And then I'm going to draw out some lessons that we learn from this point of view. I'm going to pause on a slight elaboration on L-infinity algebras, which are an instance of a homotopy algebra called relative L-infinity algebras, before finally bringing these points together to discuss some aspects of integrability. Okay, so homotopy algebras and quantum field theory. So what is a homotopy algebra? Well, informally, you could just think of this as an algebra, as a generalization of a familiar algebra to include higher products satisfying higher relations. So if you start out with an associative algebra, something that has a product that is associative, this will get relaxed to a homotopy associative algebra or an A-infinity algebra. You could do the same for commutative algebras or Lie algebras, and there is a nice machinery that goes by the name of operatic calculus that tells you how to generate these homotopy generalizations. I want to give you a little more intuition as what these higher products are, why they arise at all. And I think quite a nice way of framing this is to start with just a cochain complex. So some graded vector spaces with a differential, and I'm going to add on to it some algebraic structure, this multiplication map, that's compatible with the differential in the sense that it's a graded derivation. The example to have in mind for all of my talk is just the de Rham complex. So we have as our graded vector space just P forms, the differential is just the exterior derivative, and the multiplication map is just the wedge product, which in this case turns out to be graded commutative. So we've got an instance of a differential graded commutative algebra. Okay, so now the question that I want to ask is, if I've got one of these cochain complexes, and I've got a chain map to a second cochain complex, where the first one carried this algebraic structure, does the algebraic structure survive the cochain map? Can I transport it on the cochain map? And the answer is generically, no, you can't. Some of the properties of that algebraic structure will fail under this cochain map. So if it started out as associative, you may lose this property. And you should think of this in terms of deformation theory, right? If you deform some product, it's not necessarily true that the properties that you want of that product to survive will survive. It's just an instance of that. Can I do it on the keyboard as well? No. Of course, what's going to happen now is going to jump backwards and forwards like 100 slides, right? The suspense.
That is the pointer still working? Yeah. No, I don't think so. What is it?
So
Sorry.
I can carry on, and I think this argument isn't so complicated that you can't follow it without the slides. So, yeah. So yes, so I will fill out how it relates to the previous slide. That's the next thing that's coming up. To set this up though, what I will say is that, where I'm going with this is if you have two cochain complexes, you've got a chain map between them. If one of them has some algebraic structure, that algebraic structure isn't going to be preserved necessarily as you pass to the second one. Commutativity may fail, associativity may fail, something may fail. So in that sense, if you just want it on the nose to survive, the answer is no. Generically, the algebraic structure isn't transported over to the second cochain complex. But the answer is yes, if you allow for a richer homotopy algebra structure. And that richer homotopy algebra structure is basically going to encode the failures of the identities that you're interested in. And now I really would like the next slide. Sure, this is a good time for it.
So when you say it fails, does it mean like there exists no morphism that preserves it?
So I'm handing you two complexes. I'm handing you a chain map between those complexes. That's data you're given, and then you just go test. Does the commutative product become a commutative product under this map? And typically you'll see it fails. That doesn't mean that you couldn't find examples of chain maps that do preserve the product, right? They certainly do exist. It's just generically, there's no guarantee that they will.
There are two complexes with no morphism.
Yes, yes. Okay. So my flow has been completely disrupted, so I suggest we go right back to the beginning and start all over again. No, it's not going. There it is. Okay. Right. So there's one other slide before, but I'm not going to dare go back. The point is that these algebraic identities will typically fail. So associativity, commutativity, or the Jacobi identity, and they will fail. They will only hold up to higher chain homotopies. And these higher chain homotopies are precisely these higher products that I'm referring to. So here I'm now calling the differential M1. It's a unary operator. The original product I'm calling M2. It's a binary operator. And then I introduce an infinite tower, M3, M4, and so on. And these higher products encode the failures of the exact identities that you want to hold. Okay, so this idea is, if you wanted a more poetic characterization of what we've been doing, is this statement that the formal deformation problem infinitesimally is equivalent to an L-infinity algebra, or characterized by L-infinity algebras. So what is an L-infinity algebra? It's a particular instance of this homotopy algebra, where the algebras I'm interested in are Lie algebras. So over here, I've got the definition of a standard Lie algebra. It's some vector space with a 2 bracket that satisfies some relations, i.e. it's anti-symmetric, and it obeys the Jacobi identity. The homotopy Lie algebra, or L-infinity algebra, is a graded vector space. It has this tower of higher maps that in principle goes on forever. It doesn't have to go on forever, but it can in principle go on forever. And now rather than relations, we have homotopy relations. So I've got precise on the nodes graded anti-symmetry. That's not relaxed. But I've got homotopy Jacobi relations. They are relaxed. So here's the actual definition. Ryan helpfully said this once already. I can take a graded vector space V, and I've got these graded anti-symmetric multilinear maps, which satisfy these homotopy Jacobi relations here. I've packed them all into one thing. The only thing that you really need to absorb from this is it's quadratic in the product, right? So it looks like a Jacobi relation. So let's unpack these a little. If you just look at the lowest level, you find that mu1 is a differential. Good, we already knew that, right? I just renamed my differential mu1. Mu1 is a derivation with respect to mu2. And then here's the first interesting one. Mu2 obeys the Jacobi identities up to homotopy. So here's the standard graded Jacobi identity. I want to set it equal to 0, but this will typically fail, and the failure is controlled by the 3 bracket and the 1 bracket. And this expression here just says this is a higher chain homotopy map. Okay, the next thing I have to tell you about to be able to say anything sensible is what are the morphisms of the category of in the category of L-infinity algebras. They are a mouthful to explain. They're families of graded anti-symmetric multilinear maps that obey homotopy morphism relations. The lowest order one is just that they commute with the differentials, the kind of thing you expect. One rung up, you have the failure of phi1 to be a Lie algebra homomorphism is characterized by phi2, and so on. Okay. And special amongst all of the classes of morphisms are the quasi-isomorphisms. So the quasi-isomorphisms are those morphisms whose linear part induces an isomorphism on the mu1 cohomology. Remember, we've got a chain complex. Mu1 is a differential. There is some cohomology. I will call it H mu1 bullets for the mu1 cohomology. I want this to be an isomorphism on the cohomology. That has a physical interpretation that I will come to later. Okay, there are two important theorems associated, for me at least, associated to these morphisms. First of all, every L-infinity algebra is quasi-isomorphic to some other L-infinity algebra, which we refer to as strict or rectified or strictified in the sense that all of the higher brackets are vanishing. So anything of arity greater than 2 is identically 0. So you can always reduce an L-infinity algebra down to a DG Lie algebra. The second theorem is the minimal model theorem. And this says, it's kind of like the opposite, it's like almost complementary to this. It says that every L-infinity algebra is quasi-isomorphic to a minimal L-infinity algebra where the graded vector space is replaced by the cohomology, the underlying graded vector space. The differential is identically 0, and generically you'll get an infinite tower of higher maps, the minimal model products. Okay, and one way of explicitly seeing these minimal model products is via this homological perturbation lemma, which starts with some special deformation retract data of complexes. So I've got my minimal model over here as a complex, just the underlying graded vector space. And I've got the complex here of the original L-infinity algebra. I've got an embedding from the minimal model into the full model and a projection from the full model down to the cohomology. And I've got this contracting homotopy map here, which obeys this identity. This just says that this combination of P, then E, the projection, and then the embedding is homotopic to the identity. Okay, that also has a physical interpretation. Maybe you can see it already. Yes. It's coming. So here is so we can construct the minimal model products in terms recursively from this special deformation retract data. And I'm going to come back to this expression, so I'm not going to explain it now, and it will be addressing your question. Okay, so before I do that, so I'm going to try convince you in this next section that this statement is true, that every perturbative BV field theory is given by, I've added one word here, cyclic L-infinity algebra. So now I want to explain that statement. Okay, so let me just tell you a little bit about the BV formalism to get there. So for a classical field theory, what I'm interested in is the space of fields, but I might have a gauge symmetry which I quotient by. And then the classical observables one can think of as functions on the quotiented space of fields, quotiented by this ideal, which is generated by the equations of motion. So I want the on-shell field configurations. Okay, now this is generally a complicated object, and what the BV formalism does is it resolves it. That's its raison d'etre. So we enlarge the space of fields to include ghosts. This is the familiar BRST formalism. So we add in some ghosts which act on the space of fields. And this is technically the Chevalley-Eilenberg resolution of this gauge algebra quotient. And then we further enlarge this to include the space of antifields to give us the full set of BV fields by taking the degree shifted cotangent bundle of the space of ghosts and fields. And this corresponds to a Kozel-Tate resolution of this entire object here. Now, rather than go into the details of what all of these words mean, there's a nice way of packaging all of this up into an object known as a BV manifold. So a BV manifold is a graded manifold that has a degree -1 Hamiltonian symplectic, that is a degree -1 Hamiltonian symplectic Q manifold, which is to say it has some, you could just think of this as the BV charge, some homological vector field that squares to 0, and a degree -1 symplectic structure. And we insist that this Q is Hamiltonian with respect to the symplectic structure, which is this equation in the middle of the board here, i.e. contracting Q with omega gives you the exterior derivative of some object, and this object will be the BV action, the action that defines our quantum field theory. Okay, so how do I get over to an L-infinity algebra? Well, I use this fact that Q manifolds are related to L-infinity algebras by a duality. More precisely, an L-infinity algebra is dual to a Q manifold whose body is a point. So it's just rarely a graded vector space in this case. So if you have a Q manifold that's a graded vector space, this gives you an L-infinity algebra. This homological Q up here is just packaging all of the structure constants of the higher brackets of the L-infinity algebra up. So you can kind of see I've got these mu k's here. I've picked a basis, so there's a bunch of indices sitting on here, but these are just the higher products of the corresponding L-infinity algebra. And now those rather horrible homotopy Jacobi relations are simply Q squared equals 0. It's a very neat way of articulating things. And for the people who work with this stuff, they'll recognize this as the Chevalley-Eilenberg algebra of the L-infinity algebra. Okay, so it's just a repackaging of the same data. Okay, so I have BV manifold over a point and cyclic L-infinity algebras. I haven't yet told you what cyclic is, but in that previous slide, I said nothing about, in this relation down here between Q manifolds and L-infinity algebras, I said nothing about the symplectic structure, so I need to say something about this. This gets translated into what's called a cyclic structure on the L-infinity algebra. So here's the basic dictionary. I've got my tower of higher products from the L-infinity algebra. This corresponds to the BVQ. I've got a graded vector space. This corresponds to the space of BV fields. That's ghosts, physical fields, anti-fields, anti-field ghosts, all bundled up. I've got an inner product that obeys some cyclicity conditions that corresponds to the symplectic structure. And where I had my BV action, I've now got an object that's called the Homotopy-Maurus-Cartan action. And these are all equivalent objects. Okay, so let me work towards spelling out how to connect very concretely to a field theory. So let's just remind ourselves about not a Homotopy-Maurus-Cartan action, just a standard Maurus-Cartan action. If I have a differential graded Lie algebra, so I've got some differential and some Lie algebra with an invariant inner product, I have a cyclic structure in this and an invariant inner product that obeys these two relations. I can think of this as a cyclic structure. So it's invariant with respect to the differential, and I have this killing form type relation here. And then I can write down the Maurus-Cartan equation as a variational flat field strength where the Maurus-Cartan, which comes from the Maurus-Cartan action here. So you can imagine just varying this with respect to A, I get this equation. Now, at this stage, you should know what to do. You just replace differential graded Lie algebra with L-infinity algebra everywhere and write down exactly the same things. So I've got here a cyclic structure where I now have to consider cyclicity with respect to all of the products. Here I only had a unary product and a binary product. Here it needs to be cyclic with respect to the full tower of products. And I have a new variational flat higher field strength, which is just the sum over all of the products on some element. And I can write down the Homotopy-Maurus-Cartan action for which this equation is variational. Okay, so to make it even more concrete, here's Yang-Mills theory in this form. So I have some manifold M, I've got some color Lie algebra G, and I've got and this corresponds to some L-infinity algebra where the graded vector space is 0 forms, 1 forms, D minus 1 forms, and D forms, which corresponds to the fields, their anti-fields, the ghosts, and their anti-field ghosts. And then the Homotopy-Maurus-Cartan action comes out like this. There's extra terms here, ghost terms, anti-field terms, but it is exactly the BV action of Yang-Mills theory. And the cyclic structure is really just the pairing between, so this is some top form, you see this is a 1 form, this is a D minus 1 form, etc. And here are the L-infinity brackets that give you this Homotopy-Maurus-Cartan action. Okay, So now that was kind of like a lightning review of how the BV formalism connects to L-infinity algebras. Now I want to use some of that. In particular, I want to use the minimal model to say something interesting. Okay, so I'm now going to have some arbitrary theory written in its L-infinity algebra form, and I'm going to consider the minimal model theorem that says it's quasi-isomorphic to some other L-infinity algebra where the underlying graded vector space is the cohomology of the original graded vector space. The differential is 0, and I'll generically have an infinite tower of products. And as I mentioned, we get to this through this special deformation retract. And now in this context, we recognize mu1 as the differential operator that gives you the kinetic term in the action. So mu1 is just the differential operator of the free equation of motion. And if we stare at this equation here, we see that what H is doing is inverting mu1 up to away from cohomology. It's the propagator. Yes.
Is the expectation that everyone here you can write as a word actually?
Yes. So perturbatively. So this is all perturbative. So here we're taking like if you think of a BV manifold as being the full theory, we're looking at one particular vacuum, expanding about that vacuum and picking a point. And then yes, there's a homotopy Mauro-Cartan action for any theory. But you're raising a good point that I will come to when we discuss relative L-infinity algebras, because that's a surprising statement. And so I wonder if your surprise is going to be answered in that section. You can tell me then. Okay, so we should recognize in this special deformation and retract data H as the propagator, right? It's inverting the kinetic operator of the free equation of motion away from cohomology, because P here projects onto cohomology and then E embeds back into the full space. Okay, and then what the homological perturbation lemma, I showed you these minimal model products in terms of the original products through this recursive relation. We see this is really just a Feynman diagram expansion. So here is like the 3 bracket in the minimal model. So the V tildes are in the cohomology. They are the asymptotic physical states of the theory. They're your on-shell gluons if you're doing Yang-Mills theory. And what we do here is we embed them with E into the full space of fields. That's like a gauge choice. How do you put an on-shell physical state into the full space of fields? You pick a gauge. And then once they're in the full space of fields, we can interact them through the vertices given by the full L-infinity algebra, and then we have to project back down. But we can also do this where we take 2 brackets, and then we have to insert the contracting homotopy on the internal lines, and we rarely see it's the propagator, right? This is just a Feynman diagram expansion. So hopefully, yes.
Shows that there's like brief field theory that it's down for an early shape. Give like a formula just down for this minimal model that's you can't let those into statements about what is it?
Yes. So let me tell you, because I'm not going to talk much about strictification, so let me deal with that one first. You can think physically of strictification as introducing auxiliary fields to reduce all your interactions down to purely cubic interactions. So for any field theory, you might have like well, I don't know why I'm trying to be elaborate. You could have a 4-point interaction. You might want to introduce an auxiliary field to reduce it down to a 3-point interaction. That's like the physical articulation of the strictification theory. So in general, let's say if you have the principal chiral model, or well, yeah, you could be in the situation where you need an infinite tower of auxiliary fields, or you might find some clever realization where you just need 1 auxiliary field. So the generic theorem, this general phrasing typically introduces an infinite tower of auxiliary fields to do this. So that's strictification, reducing the vertices, the interactions, down to purely cubic vertices. The minimal model here, which is I'm going to explain a little more as we go along. So let me just do that through the slides, and then if you still have questions, come back to me. So what we see is that if I then use the cyclic structure to pair the minimal model brackets with a final outgoing on-shell physical state, I rarely get the tree-level scattering amplitudes. So hopefully that answers your question. The minimal model corresponds to the tree-level scattering amplitudes. And the homotopy-Maurer-Cartan action of the minimal model is just the generating functional of the S matrix. And so in this sense, actions and amplitudes are rarely unified as quasi-isomorphic L-infinity algebras. You give me an action, it relates to some cyclic L-infinity algebra. There's some quasi-isomorphism to the minimal model cyclic L-infinity algebra. They are quasi-isomorphic L-infinity algebras. One is the generating function of the S matrix. The other is your original action defining the theory. So that's what I meant by we really unify this on-shell picture with this off-shell picture. They're quasi-isomorphic pictures. Okay, and once you have that picture, you can start saying, well, what in quantum field theory can I do in L-infinity algebras? And you can kind of, go down your favorite topics and construct a list of things to consider, whether this be Witten diagrams and I'm going to focus on color kinematics duality, which I've left off of this, but this is the closest, the double copy. Okay, so there are various things you can then start thinking about putting into L-infinity terms. So let me give you the example of color kinematics duality. If you take, say, just Yang-Mills theory for simplicity, and you can always rewrite the scattering amplitudes of Yang-Mills theory in this kind of form here, where you have a sum over purely cubic diagrams. I'm not going to focus on the details, just to note that there is a color factor which is built out of the structure constants of the color Lie algebra, and then these kinematic numerators here, which are built out of the kinematic data, the polarization tensors and the momenta of the gluons that you're scattering. So we've got color and kinematics. The duality conjectured by Bern, Carrasco, and Johansson is that whenever a triple of diagrams satisfies a Jacobi relation, there is a rewriting of the amplitude such that the corresponding kinematic factors obey the same identity. This is a kind of a non-trivial thing. It's not obvious that this is true. You have to work to prove it. There are many other perspectives on color kinematics duality. I'm not going to tell you about any of them, but you can have a look at Eric's recent review, which is based on some lectures he gave as a kind of semi-outreach type thing. So it's a bit of advertisement there. Okay. This suggests, we've got these Jacobi identities for color, and then the kinematics is obeying the same Jacobi identities. It suggests that there is some hidden kinematic Lie algebra somewhere. You see a Jacobi identity, there should be a Lie algebra. But it's certainly not manifest in the action. Now, we're in this situation where we've got some relations that are not manifest. We should resolve to see those relations, right? This is the lesson I'm trying to impart here. And indeed, you can do this. So one can show that if you have tree-level color kinematics duality, there exists a quasi-isomorphic L-infinity algebra, let me call it LCKD for color kinematics duality, with new higher products that encode the color kinematics duality. So they make the color kinematics duality manifest. You can then do this rectification, this strictification thing. So these products will generically be higher. They'll generically go to all orders. And then you can strictify to reduce them down to just purely cubic order. And you land precisely on a Lie algebra structure where so when you color strip, this is now a C infinity algebra, or it's actually just a DCGA, and it's dual to a kinematic Lie algebra. So we learn that color kinematics duality is an ordinary, potentially anomalous symmetry of the BV action. You just have to find the right L-infinity algebra expression of it. Okay. We can go a little further with this. Mikhail Reiter has this very nice paper in 2018 where he showed that color kinematics duality of four-dimensional Yang-Mills theory for the tree-level S matrix is equivalent to what he called a BV box infinity algebra. So it's another type of homotopy algebra. We then generalize this to the off-shell situation for actions and constructing an off-shell BV box infinity algebra, and the kinematic Lie algebra, the existence of a kinematic Lie algebra corresponds to the fact that if you color stripped your L infinity algebra, you factored out the gauge group, the thing that you're left with isn't just a C infinity algebra, it's actually one of these BV box infinity algebras. That's what color kinematics duality is from this point of view. And recently, Madonas and Vallette wrote a nice paper where they constructed this BV box infinity algebra as a co-fibrant resolution of the BV box operad for the experts in the audience. Okay, and then you can rectify this BV box infinity algebra to give you a strict BV box algebra where you just have a two bracket, this box operator, and a degree -1 unary operator. I'm not going to tell you about the details of this. It's not important to the integrability story. But you see, you get this kinematic Lie algebra coming from this degree shifted derived bracket. Okay, so I wanted to say all of that just to impart a lesson. We want to lift hidden symmetries to some homotopy algebra structures. That's the partial lesson I want to communicate through that. This is very nice, but none of this gave us any closed form, and it was potentially anomalous. So we want to maybe do a little better. How can we do better? Well, we can look at a paradigmatic example, Chern-Simons theory. This has full off-shell color kinematics duality, which implies it carries a BV box algebra structure. And in this case, it's very simple. So just to remind you what the L infinity algebra structure of Chern-Simons is, it corresponds to a strict L infinity algebra. This means it only has a two bracket. That two bracket is the wedge product. That makes sense, right? The graded vector space is given here. It's just naught forms, one forms, two forms, and three forms: ghosts, fields, antifields, antifield ghosts. And then if you turn the handle, you get the homotopy Maurer-Cartan action. And if you color strip, so we factor out the gauge Lie algebra, you get a strict graded commutative algebra, differential graded commutative algebra, where the differential is the exterior derivative. And this B operator that I wanted is now just the adjoint. And then we see that this relation that you needed for color kinematics duality is just Hodge theory, right? It's just that the commutator of D with D dagger is the D'Alembert. So Chern-Simons actions give you very nice characterizations of this hidden symmetry. So lesson 1 is look for Chern-Simons type actions. Okay, hopefully you can see where I'm going with this. Yes. Yes. So for Yang-Mills theory, we can do it order by order. So it's constructive in the sense that if we know the action up to some order, we can build the next term in the action. For South-Joule Yang-Mills theory, we've got a closed form expression. I'll tell you about that in a moment. It's my final lesson. For Chern-Simons, it is just the Chern-Simons action itself. For full Yang-Mills, there's a BV box algebra structure, but it doesn't manifest color kinematics duality. This is a long story. I could be happy to talk to you about it. Okay, so for Chern-Simons, so now we come to holomorphic Chern-Simons theory on twistor space. This lesson was look for Chern-Simons type actions. I have a Chern-Simons type action for supersymmetric South-Joule Yang-Mills theory. Okay, I haven't got anywhere near integrability. Okay, I better hurry up. Right, so here is the BV action, and this B operator that we need exists. Let me cut the story short. It anti-commutes with the with del bar to give me the D'Alembert, and this implies color kinematics duality. And what's interesting about this is you can imagine Kaluza-Klein expanding the Chern-Simons 1 form on the CP1. It gives you this infinite tower of fields. This is the infinite tower of auxiliary fields that we needed to introduce to manifest the color kinematics duality. So they've been geometrized. So this is going to be my final lesson, is I want to look for auxiliary spaces that geometrize the hidden structures that we're after. Okay, now given, okay, I'm going to pass over relative L infinity algebras. This is about how do you introduce boundary terms, and it relates to your question about homotopy-Maruc-Cartan actions. So without this extra wording about relatives, there is a discrepancy between homotopy-Maruc-Cartan actions and a generic field theory, and that's what the relative is meant to be fixing here. But I will make some comments at the end, but I'd like to tell you about how we connect to integrability. Okay, so I'm going to focus on the principal chiral model for simplicity. I'm really an imposter in the integrability universe, so I have to do something I understand. And we have this nice story that the conservation and flatness of the current J combines into a one-parameter family of flat connections. And this implies the existence of an infinite tower of conserved charges, which are generically non-local. Away from the lowest order, where they're Noether charges, these are hidden non-local symmetries, and it makes you wonder, we've got some hidden symmetry, less than zero, should there be some homotopy algebra structure behind all of this? Or you could accuse me of, this saying when all you have is a hammer, everything is a nail. But of course, I wouldn't be standing here telling you about this if there wasn't something to say. And indeed, there is quite a lot to say. There are these very nice works by Benoit and Alex and Marco and Ryan, a new collaborator in this story. And I'll refer you to Ryan's very nice talk for more on this. So indeed, there is a lot to say about homotopy algebras and integrability already. Okay, so here are my lessons from color kinematics duality. If I've got some, I should identify some hidden structures, and I should understand them in homotopy algebraic terms. And then I should look for Chern-Simons actions, and then I should look for auxiliary spaces which, encode those relations. And I just want to apply the same lessons to integrability. So here I've got a hidden kinematic Lie algebra, here I've got a hidden tower of charges, and I've got these two question marks, but actually, as we saw yesterday, all of this work has already been done for me. It's 4D Chern-Simons theory. There are many other ways you could have done it. The one I'm going to pick on is 4D Chern-Simons theory. So I will be very brief here because we saw this a few times. So I will refer you to the really nice talks of Mir, Ryan, Lionel, Anders for much more on this story. There are many experts you can quiz about this. I've been quizzing experts this week. It's been very helpful. So 4D Chern-Simons, we have like the standard Chern-Simons action wedged with a meromorphic one form that gives us the measure, and the poles of this meromorphic one form really determine what kind of 2D model we get. All the dynamics are localized on the pole, on the poles. So it's topological away from the poles. And this CP1 is it's geometrizing the spectral parameter. So it's a very nice story in that sense. Okay, so given that this already exists, our task is simply to show that the cyclic L-infinity algebra of the principal chiral model and the cyclic L-infinity algebra of the 4D Chern-Simons theories are actually quasi-isomorphic. That becomes our task in this case, because all of the other work has been done. How does this go? Well, what we need is L-infinity algebras for the PCM and 4D Chern-Simons. We need their cyclic structures, and we need a quasi-isomorphism relating them. And this is where most of the work goes. And then the lax connection will appear in the image of the quasi-isomorphism. So here's the graded vector space for semi-holomorphic Chern-Simons theory. It's basically the same thing as I had for Chern-Simons theory, except for I split the one form into components living along sigma and components living along the CP1. And then there is a long list of boundary conditions that basically just ensure that this theory is that the cyclic structure is cyclic, that the products of the fields don't leave the field space, and that yes, I'll come to the differential in a moment. So much of the work is just in identifying the appropriate boundary conditions, but I should say that these are more or less just read off of Sylvan's review. So there's nothing really novel here. Okay, so now we need to write down what the differential is. We introduce a regularized anti-holomorphic derivative so that we don't introduce higher order poles through the differential. We have the higher products written down explicitly, so this is just some kind of more elaborate form of the wedge products. And then we have a cyclic structure, which is kind of the obvious thing that Ryan introduced yesterday as well. And then we get this BV action. So this is what it looks like, and it really does just look like the Chern-Simons BV action with a anti-holomorphic derivative that's regularized wedged with this meromorphic one form. Okay, we'll then go to this choice of writing G as the exponential of some field and write the PCM action in this form. We need it in Mauro-Cartan form, so we'll integrate by parts. And then we get these higher products for the PCM. And we have a cyclic structure. We will flip to the Chevalley-Eilenberg picture because it makes expressing the quasi-isomorphisms very easy. So in the Chevalley-Eilenberg picture, we'll start out with the PCM. We'll go to some new version, which is just an isomorphism. And then we have a morphism of differential graded algebras in the Chevalley-Eilenberg picture between the semi-holomorphic Chern-Simons theory and this new version of the PCM, where the lax connection appears in the image of this quasi-isomorphism. Okay. Composing this with the relation between the two PCM models, we get an explicit quasi-isomorphism between the L-infinity algebras. Yeah. Okay. So outlook. One question we asked ourselves was, does this quasi-isomorphism arise from homotopy transfer, as in the work of Benoit and colleagues? And I think if I understood them yesterday correctly, the answer is yes, they showed this explicitly. I think that's a correct statement. You might think about applying this to other places like higher dimensional 5D Chern-Simons theory, and encoding as L-infinity spans the web of relations amongst various different integrable models this way. I will end on going back to this relative L-infinity algebras point of view. This will be my last slide. That the idea of the relative L-infinity algebra was to have manifolds with boundary. And one way you might think about the 4D holomorphic Chern-Simons theory is, rather than having poles, actually have little disks cut out and then have a boundary theory there and put a topological boundary theory encoding the boundary data and then shrinking the disk down to recover the PCM. And in that way, we would really be applying the homotopy transfer of the relative L-infinity algebra, which I appreciate I didn't tell you about. And this suggests some novel way of realizing 2D dualities in terms of the relative L-infinity algebras and their four-dimensional parents. So I will stop there. Thank you.
Thank you for the nice talk. We have time for one or two quick questions.
So I agree that it's a very nice formalism and a very nice framework to understand aspects of quantum field theory and to perhaps identify some quantum field theories with others. Does this give me something perhaps new that I wouldn't be able to see without using this formalism? Because I agree that some of the examples, for example, the color kinematic duality, people had actually found it, and then you formalize it for the Chern-Simons. It was also found, and then you can, like, everything fits very nicely. The question is, if I wanted to convince myself to learn this formalism, is there an example in which there was something clearly new constructed from it?
So I guess the cheapest answer to that is new color kinematic examples of color kinematics duality. So once you've understood that color kinematics duality corresponds to the color strip C infinity algebra carrying a BV box infinity algebra structure, proofs of color kinematics duality can almost be trivialized if you can find the right formulation. So an example of this is M2 branes were conjectured in 2012 by Tristan McLaughlin and others, Henrik Johansson, to have a color kinematics duality 3 algebra structure. Now, it turns out if you follow this point of view that I've just been expressing, in a few lines, you can prove this conjecture. So they showed it up to 8 points, and you can also prove but you can prove it in generality, and you can also show that it actually reduces to a standard kinematic Lie algebra rather than one of these exotic 3 algebras. So once you've understood the structure, you want to turn it around and say, now can I discover something new? Another example would be loop BG recursion relations in scattering amplitudes for more generic theories. I think in various contexts, I mean, like, it depends how demanding you are of what is really interesting, but in various contexts, you get new things. So for example, there's this story of generalized symmetries, and from this point of view, it becomes clear that there are other kinds of generalized symmetries that one wouldn't see if one didn't go to the graded homotopy algebra picture, kind of ghostly generalized symmetries. So yeah, I mean, I think you're absolutely right. The proof is in the pudding. One really wants to see what one gets from this in the end. Yeah.
Hi, thanks for a nice talk. I wanted to ask you if all of these Paul conditions that you have, you formalize it in the relative L infinity setting?
That's a really good question. So that's like the next on the to-do list. I don't know is the honest answer. We just have to sit down and try. I mean, the expectation is, so there's this general philosophy that if you have a field theory on a manifold with boundary, the boundary conditions can be encoded in a topological field theory living on the boundary. So just running that general philosophy, I want to say the answer is yes, but I shouldn't say it's yes until we've actually sat down and done it.
Thanks.
Well, I guess I have a very simple question. The Chern-Simons action is not gauge invariant. How can you see it by using the L infinity formalism?
No, so it seems like skipping over the relative L infinity algebra story was a mistake. There's lots of questions relating to this. Yes, you're right. So it simply wouldn't be so first of all, I should say that the full BV formulation, so for a BV manifold, exists for Chern-Simons theory. And there, it's not different to what you have in your mind. It's exactly the same story. Here, perturbatively, if you had a boundary, you would see that the cyclic structure would fail to be cyclic. And that would just be encoded, that would be, that failure of cyclicity would be the lack of gauge invariance. But this is really this story about integrating by parts and seeing that you get something non-gauge invariant. But yeah, it's the failure of cyclicity, and there's two ways of addressing this. There's the BFV formalism, which is like a grand, rather elegant structure where you can do this. The relative L infinity algebra story is a very mild generalization of that once you've gone to the perturbative setting. So we're firmly perturbative, and we have a mild generalization of that issue, where you reintroduce cyclicity by introducing these boundary field theories, and you could have in mind that you would have some theory living on the boundary to fix up the lack of gauge invariance.
Well, I don't want to say that Chern-Simons theory is not gauge invariant unless give it one so how can you deal with that?
Yeah, so that's, for the in the perturbative setting, we don't see that fact.
Okay, then let's thank Leron again.